The next random variable is a triangular random variable. This random variable is especially important for simulation modelers. It is a commonly used type of distribution to model the input variables when we do not have enough data about input variable. However, we have expert opinions about it. So what is the triangular distribution? First of all, the probability density function for a triangular distribution obviously will have a triangle shape, right? So if we call it a triangle distribution, it's not going to have any other shape. A triangle shape we will have, and the area under the PDF is going to be equal to 1. Do not forget about this. This is the golden rule of the PDFs. And there are 3 parameters for that distribution. The least possible value, the largest possible value, and the most likely value. So A here is the least possible value for that random variable to take, and C is the largest possible value that it can take, and B is the most likely value that it can take. Now, if we want the area under this triangle to be equal to 1, then the height at B should be equal to 2 over C minus A, and the PDF will consist of 2 piecewise linear functions here. Now, between A and B, the linear function is going to be equal to 2 times x minus a divided by b minus a times c minus a. And in the second part, there will be a decreasing function with a negative slope. And between b and c, the linear function will be 2 times c minus x over c minus a times c minus b. And the CDF is just going to be the integral of the PDF here. The first component, the first linear function here will be integrated as a convex quadratic polynomial, the second order. And in the second part, we are going to have a concave quadratic polynomial. And for values that are less than a, we will have 0. For values which are greater than c, we will have 1. And of course, just like the PDF is piecewise defined for 2 intervals, CDF is also going to be piecewise defined, but in quadratic polynomials. The expected value of a triangular random variable would be equal to a plus b plus c over 3, and the variance would be equal to a squared plus b squared plus c squared minus the product of each dual combination of these 3 values. They are separately subtracted, and that value is divided by 18. Now we are going to solve an example about a triangular random variable. It says the duration of a certain task is bounded within 3 and 8 hours, and the most likely completion time is set to be 5 hours. So this means what? This duration is bounded between 3 and 8 hours. So the least possible value is 3 hours, the largest possible value is 8 hours, and the most likely, the mode of this distribution would be 5 hours. And because we are talking about the duration here, it is a measurable quantity, therefore it should be modeled with a continuous random variable. And we are emphasizing that we are assuming a triangular distribution, which means, so we are going to have an increasing linear probability density function from 3 to 5, and from 5 to 8, we are going to have a decreasing linear function. What is the probability that the duration of the task will be between 40 and 360 minutes? Now, my friends, first we determine that x is a triangular random variable with 3 parameters: the least possible value, the largest possible value, or the minimum observation, maximum observation, and the most likely observation, basically. And we are looking for the probability of x to be between 240 and 360 minutes. However, we are defining this random variable in hours, so we need to be very careful about the time units, my friends. So if we intend to calculate the probability of x to be between these 2 values, then we are going to find something very wrong. So what we are going to do is, we are going to convert these 240 and 360 minutes in hourly units, because the way that we have modeled this random variable was hourly. Okay, so the parameters are defined in hourly units. So 240 minutes is 4 hours and 360 minutes is 6 hours. We are looking for the probability of x to be between 4 and 6. Either we integrate the PDF between 4 and 6, but this requires a partial integration. From 4 to 5, we integrate the first part of the triangular probability density function, and from 5 to 6, we use the second part, because 5 is the separation point of the piecewise linear functions of the probability density function. So the result will be a 19/30. Or you can directly use the CDF as it is defined in the previous page. You need to calculate F6, and then you calculate F4 and subtract it from F6. Now, for F6, you need to use the second part. Since 6 is greater than the mode 5, you need to use the second part of this cumulative distribution function. But for F4, you need to use the first part, and the difference would give you again a 19/30 as a result.